Okay, let's let's start. So let me start with a quick introduction of Dr. Ebru Bozdag. So Dr. Ebru Bozdag is an assistant professor of geophysics, also affiliated faculty to the Space Resources Program, and researcher in the Center for Space Resources, and faculty fellow of the Payne Institute at Colorado School of Mines. Her research interest lies in computational seismology. She uses 3D numerical seismic wave simulation to improve understanding of Earth's interior by linking observed data to advances in theory and numerical methods in wave propagation and optimization techniques. Her primary focus is on full wave inversion, with a special emphasis on global seismic tomography based on 3D seismic wave simulations and adjoint techniques. In recent times, she is also involved in exploration scale problems and planetary seismology as a part of the Mars Insight mission. So welcome, Dr. Ebru Bozdag. It's over to you.
So thanks very much for the invitation and for the nice introduction. So let me put everything in the presentation mode. Can you still see everything without any problem?
Yes.
Okay, perfect. So I'm going to talk about our efforts to image, primarily in imaging Earth's interior, but also I will talk about some of the results from the Mars Insight mission. Based on, my primary tool to investigate Earth's interior is 3D wave simulations. And as you also mentioned, my ultimate goal has always been to perform full waveform inversion at the scale of globe to image Earth's interior from surface all the way down to its center. So here you see the crowded people of my collaborators, past and present collaborators. And this is basically what I will be focusing on today. So here you see a cartoon image of Earth's interior showing the very thin crust, the mantle all the way down to core mantle boundary, the fluid outer core and the solid inner core, where the fluid outer core is the main cause of the generation of the Earth's magnetic field. And there are also lots of interesting geodynamical processes going on in the mantle, which are also driven by the core, where the core mantle boundary is the main thermal boundary, where the convection currents in the mantle is responsible for the plate tectonics and the earthquakes and the volcanic activity that we see at the surface, which are directly controlled by the subducted slabs, the cold subducted slabs, and the hot material and low wave speed materials, which are called mantle plumes, which we think that they are originated from core mantle boundary and go all the way up if they could reach the surface, generating hotspot related volcanism in the Earth. So initially, because of the resolution of our global simulations, our goal has been to image from surface all the way down to core mantle boundary. So we perform these 3D wave simulations and full waveform inversion, also including the core. I mean, in our numerical simulations, we have the core. However, we just keep it just radially symmetric 1D core without updating. We only try to image the patterns in the mantle. But of course, our ultimate goal is to also investigate and image the Earth's outer core, which we just started exploring how we can do this by going down to 9 seconds in our simulations. And of course, the ultimate goal is to go down to 1 second in numerical simulations to image image inner core, basically performing a whole Earth tomography. However, I have been pretty optimistic by writing that this is the subject of exascale computing, which is there. Now we have the exascale computing resources, but most likely if you would like to do everything in the brute force approach, still it's not feasible to invert, to perform full waveform inversion with simulations down to 1 second. We can discuss more if you like later on. So First of all, I would like to summarize what has been done classically in global seismic tomography to image Earth's mantle. So generally, this procedure involves starting from a radially symmetric Earth model, such as PRAM. The goal is to try to model the lateral variations in the mantle through seismic modeling. And this process traditionally has been based on ray theory, which is a great theory. And actually, we have most of our understanding about the Earth's interior. It's coming from ray theory. However, it has some limitations because we are working with band limited data. And when we would like to increase the resolution further, we need to take into account the finite frequency effects, which have been taken into account in the recent tomographic models, either using 1D background models or incorporating 3D wave simulations. So typically, body wave travel times or surface wave group and phase velocities, normal mode splitting functions, and some of the waveforms of S waves and surface waves have been used or have been incorporated in imaging to try to improve the data coverage. And another important aspect is that most of the global mantle models, they have crustal corrections. So we are now at a stage where details matter, because as I said, if we would like to further improve the resolution of these images, we need to start avoiding approximations and corrections as much as possible. Finite frequency effects are one of them. Here you see a nice illustration of the finite frequency effects for an S wave. Assume that you have a source here and a receiver here. So ray theory tells us that in a radially symmetric model, the waves will follow the ray path like this. And we assume that the waves are sensitive to the structure along the ray path. However, finite frequency theory tells us that since we are working with band-limited data, paradoxically, our seismic waves are not sensitive to the structure along the ray path, but the structure around it, around the Fresnel zone. And if you take a cross-section orthogonal to this, you see such a hole-shaped structure where the center has zero sensitivity. So just because of this nice shape, this theory has been also known as the banana donut theory for body waves. So that's why we need to now incorporate 3D wave simulations in the computation of seismograms and pressure sensitivity kernels to construct our 3D models. So data coverage has been the long-standing problem at the global scale because our main seismic sources are the earthquakes, and they are typically located at the plate boundaries. We don't have earthquakes everywhere. And if you look at the distribution of seismic stations, this figure on the right shows the global seismographic network stations. We have most of the stations naturally in the continents and in the northern hemisphere. And nowadays, of course, we have these excellent dense seismic networks in the continents, such as the US array or the European stations or Chinese networks or Japanese networks, etc., which offer excellent opportunities for us to image the lithospheric and upper mantle structure underneath continents. However, such dense continental networks also introduce extra challenges for global tomography by biasing the resolution, especially in the oceans where we have lack of stations. So the ultimate goal is to deploy ocean bottom seismometers everywhere in the oceans, which is the dream of every global seismologist, I believe. However, it's costly and we don't know how we can really achieve these Pacific array or Atlantic array dreams, true. But there are other instruments, promising instruments to sample oceans, such as these acoustic floating robots, mermaids, where one of my students is currently working on this to try to incorporate mermaids data in inversions. We are still exploring. Or the new technology, distributed acoustic sensors, which have been demonstrated with the submarine cables and in the continents pretty nicely. This figure shows, this is from Mara et al. I'm sorry for missing the citation, showing the underwater fiber optic cables. So if we can make use of them, they can also potentially provide us data to sample the oceans better. However, at this stage, we cannot change this distribution dramatically, maybe in the near future, but we can use as much as data from a single seismic trace to further improve the resolution. So actually, we have now, I mean, as a global seismologist, I can complain forever about the lack of data or insufficient data, but actually we have a lot of data that we don't know how to deal with. So this is kind of the big data challenge in seismology that we are facing with nowadays. But on the other hand, on other planets, we have the opposite problem. We have lack of data. So after the Apollo mission, finally, the InSight mission has deployed one very broadband seismometer on Mars, but it's just a single seismometer that you see here. So we have small data problem on the other planetary bodies. So, but still, we should not underestimate the power of a single instrument. You can still, it's very amazing. You can still do a lot of exciting stuff. For instance, this was an earlier understanding or estimation of the Mars interior about the core size, and there have been all these discussions if the Mars has a solid or liquid core, what is the crustal thickness, and where is the core mantle boundary, etc. And actually, with the InSight data, very recently, these there have been three science papers published. Here you see the results, the main results in summary from two of them. Now we have better constraints on the crustal thickness, which is now thought to be between 24 to 72 kilometers. And actually this range is also related to the structure right underneath the InSight lander. But actually, we know that the crust has a huge effect on specifically surface waves, but actually all types of seismic waves, which is much more crucial for Mars because there is this crustal thickness dichotomy between the northern and southern hemispheres. But this just gives us an idea about the crustal thickness underneath the lander. And another important constraint provided by this mission is about the size of the core, now which is estimated to be within this range. And of course, we still cannot comment on the existence of solid inner core. Most of the geophysical modeling from other data types as well suggest a fluid core for the Mars interior. And here you see a comparison of the seismic waveforms, Martian waveforms from InSight missions. These are the published ones, that's why I can show them. All these events happened about 30 degrees away from the InSight lander in the Cerberus Fossea. And if you look at the data from 4 Marsquakes, almost happened, they are all from this region. Actually, first of all, the first observation is that they look different than earthquakes because there is much more scattering. And another important observation is that we don't observe significant surface waves, or actually we are not convinced yet if there are surface waves in the Marsquake data. So actually this strong scattering in the Martian data tells us something about the Mars interior. Most likely there is less water, more, which causes more scattering, etc. And now we have also, I mean, these Marsquakes have been relatively small, like maximum magnitudes 2.7, but also please consider that the Mars is almost half of Earth. So a magnitude 5 Marsquake would be really great, can provide really good data compared to Earth, especially when you look at teleseismic paths. And we now have some larger Marsquakes recorded, and just on the 1000th day of the deployment of the instrument. So right now the team has been analyzing all these larger quakes, which are also apparently estimated to be a bit further away, not only from Cerberus Fossea. So what I am doing with my group is, again, we are trying to incorporate or take the advantage of 3D modeling to further analyze these seismograms. So for instance, here you see our efforts to simulate something similar to what we are observing as Mars data. But for instance, the first seismogram is from one of the radially symmetric, but an old radially symmetric Mars model, which generates such a response. But as soon as we add a two-layer crust from the receiver function analysis, together with 3D MOHO variations and topography, you see how the seismograms become much more complicated or gets closer to what we observe. Of course, there are other issues. As I said, there is no, we don't observe strong surface waves on Mars data, and most of our reference models generate beautiful surface waves. But we also try to understand how we can destroy these surface waves. So one simple explanation might be about the depth of these quakes. Unfortunately, we cannot comment much on that because we have only a single instrument. But also maybe one of my postdocs right now, he's working on seeing the effect of scattering on surface wave propagation. And here you see how the crustal thickness from in the north-south and east-west can change the waveforms, especially the surface waves. And here, this is a nice movie that we prepared together with my collaborator, Daniel Peter, showing the effect of 3D crustal dichotomy on seismic wave propagation of Marsquakes. So here you see, actually, I basically initiated a source at the location of the lander, and our model is radially symmetric Sol spawn model, but we just superimposed the crustal thickness variations and added the surface topography. So whatever you see in these simulations, all the variations in the seismic wavefronts is coming from the crust and topography. So this is the P wave, and then followed by S waves, and then finally you see the surface waves. And if we continue simulations, here I would like to stop. This is Hellas Planitia, which is the largest crater on Mars, where we have the thinnest crust basically in our model. So you can see how the surface waves speed up. Actually, these are radio waves. They speed up when they pass through this crater because there's thin crust that the surface wave starts propagating with the mantle speed. Whereas you see all the distortions along the wavefronts just coming from the crustal thickness. I will just let you see the full movie. And here you see the antipode, and then you start observing the propagation of the multi-orbit seismic waves. Okay, so we can, now we are routinely running these simulations on Earth. And if we just record these wave simulations with the seismic stations, this is basically what you are seeing as seismograms here. You see a sample seismic record section for an event in Argentina. It's a deep event. And here you see the epicentral distances of the seismic stations, and the station codes are given on the right. The black seismograms are the observed ones, and the red ones are the simulated ones. So basically, we used a 3D Mantle and Crustal model. This is S362 INE plus Crust 2.0, which is also the starting model of our full waveform inversion modeling. And I filtered the seismograms between 17 to 60 seconds. So what we see here is that basically we have a pretty nice match between the observed and synthetic seismograms, especially on the body wave part, right? And you see the major phases labeled. But when we run into the surface wave regime, of course, we start seeing quite some differences between the observed and synthetic seismograms. But actually, this is where our job starts. Basically, our goal is to make these measurements and then try to minimize the difference between these observed and synthetic waveforms. And I also would like to add that this is a really nice earthquake, a very clean earthquake, because it's a deep one. And not all our data is that well, mainly which are where the waveforms become much more complicated, especially for shallow earthquakes. So, so actually in our modeling, the advantage in the full waveform inversion is that in the classical seismology, we have to, I mean, if you are using a ray theoretical approximation, etc., of course, you need to be able to model all these phases. So typically, the modeling is limited to major arrivals like major P arrivals or some core reflections or S waves or the surface waves. But the nicest part of full waveform modeling, where you incorporate 3D wave simulations, is that now we can use anything and everything. So in the ideal case, we can use the complete seismograms on 3 components, which dramatically increases the data coverage. So another problem is the crust, which can be highly nonlinear. That's why I said that the seismologists prefer to apply crustal corrections. However, in the crustal corrections, there are 2 major assumptions. One of them is that seismologists think that they know the crust. So for instance, this is Crust 2.0, one of the models which is commonly used. And the second biggest assumption is that we can compute the crustal phases based on first order approximations. However, crust can behave really nonlinearly because the crustal thickness variations crustal thickness can vary from 7 kilometers underneath oceans, which can be up to 70 kilometers underneath continents such as Himalayas or Andes, which cause lots of nonlinearities. And actually, here I would like to show something that this comparison from Chang et al.'s paper. You see different mantle models from different groups showing the upper mantle radial anisotropy. I'm not going to go into details of this figure. What I would like to highlight is that if you look at the upper mantle anisotropy from 100 kilometers down to 600 kilometers from different groups, you see significant differences. You know, these models significantly differ from each other and there is no consensus. So one of the consequences of imperfect crustal corrections is that most likely the uncorrected crustal signal can contaminate to the upper mantle, and where the major concern would be on the anisotropic interpretations. So that's why crust must be addressed properly in inversions, and that has been the motivation for us to perform these large-scale simulations. So in the what we call global adjoint tomography is an inversion, full waveform inversion technique, where we simulate forward simulations and fresh sensitivity kernels in realistic 3D Earth models using a spectral element method and using the adjoint method for the inversion part. And the crust and mantle are inverted simultaneously, so we can avoid crustal corrections. And using this technique, we constructed the first generation models with transverse isotropy in the mantle. These are OPS wave speed models. And the first global adjoint model is GLAD M15, which is the result of 15 conjugate gradient iterations. And then GLAD M25, the successor of M15, was performed with 10 more LBFGS type of iterations. And of course, now what is next? We continue improving these models by taking better physics in the inversion part, like addressing general anisotropy, analasticity, or better addressing source effects, etc., while we try to incorporate more and more data. So just a brief background, what is the adjoint method, what it does, and how we compute, or what is the advantage of it. So basically, the adjoint method is a mathematical tool, a useful concept for us to that allows us to incorporate 3D wave simulations in seismic tomography. So basically, we can compute the gradient of a misfit function numerically by using this method. So this is just a nice illustration by Carl Tape, how we compute the gradient of a misfit function. So assume that you have a source, let's say an earthquake source here, and a seismic station here. Let's start from here, bottom. And you initiate your source, and in this 2D example, you generate an S wave like this. And then there's the free surface boundary condition that you have the reflection from the surface, which becomes SS wave. So this is S wave and this is SS. And after a certain amount of time, your receiver records S and SS phases. And now let's repeat the same simulations, but this time by making some measurements. We record the seismogram here, and then we compare it to observed data. We define a misfit function and measure the difference between observed and synthetic. And now let's use that misfit between the observed and synthetic as a fictitious seismic source, located this time at the location of the receiver. And let's initiate the same simulations backward in time, which is initiated by this fictitious source. Again, we generate the S wave. Again, we have the reflection from the surface. And this time, let's record it again by a fictitious seismic station, but this time located at the location of our regular seismic source. And the only difference between these two simulations is the source term. As you see, using the reciprocity, the Green's function is the same, but the source term is different. And if we just look at the interaction of these two wave fields, but the second one is now called adjoint wave field. If we look at their interaction and then integrate over time, then we basically compute what is so-called banana donuts or the Freshe sensitivity kernels, or basically this is nothing else but the gradient of your misfit function. If you perform this in 3D, then for a well-isolated P wave, you have these banana donut sensitivity kernels. And of course, this is frequency dependent. This is filtered down to 27 seconds, 18 seconds, and 9 seconds. As you go down to lower periods or higher frequencies, in the high frequency limit, of course, these sensitivity kernel will collapse on the ray path, which will give you the ray theoretical results. And if you perform this for all the measurements from all source station pairs and sum them up, that is going to give you the gradient of your misfit function. And then once you have the gradient, then you can update your models iteratively using gradient-based optimization techniques. And for GLAD M15, we started these simulations from a 3D background model, S362 INE plus CRUS 2.0. And in our simulations, topography, bathymetry, attenuation, ellipticity rotation, gravity, and ocean load, they are all included. The length of seismograms is now 180 minutes to capture the multi-orbit major arc surface and body waves. At the beginning, the resolution of our synthetics were 27 seconds. Now it's 17 seconds, and we started exploring 9 seconds as well. So we are using these high performance computers. Initially, I mean, these two models were constructed using Oak Ridge National Labs Titan and Summit systems, and we are using SpecMem 3D Globe, the free software available from CIG. So just a background information, the first global seismic models came out in 1984 by the Harvard group and the Caltech groups. So these are the first images of the Earth's mantle at the global scale. So apparently these and these are the first colorful images of the Earth's mantle. And apparently this 1984 was kind of a very productive year. I have no idea what happened here with the text. Actually, I didn't want to erase anything but highlighted. I'm sorry about that, but I can tell you what it is. Albert Tarantola, an exploration seismologist in 1984, he just gave the recipe of the adjoint inversions. He just wrote in his paper that basically he's the one who introduced adjoint methods into seismology. He just said that, okay, if you would like to do all these things properly, here is the recipe. And this was more than 30 years ago. And just 2 years later, in 1986, they applied this full waveform inversion to a 2D problem to image this cylindrical body. And this is what they obtained after 5 iterations. And at that time, they used the high performance computer of Total and performed these 5 iterations. But eventually, they concluded that the main limitation is the memory and the storage requirements. So at the moment, we cannot do any better. We need more computational power. And indeed, that has been the main limitation why these techniques could not be applied to global scale. So here is a comparison to give you an idea about what they did in 1987 and with this 2D problem and what we tried to do in more than 30 years later in 2016. So in their problem, it's a very small but 2D body. It's like 1 kilometer by 1 kilometer model, which had, in our case, we have the entire mantle and the crust. They had 200 by 200 grid points. In our current resolution, in the construction of GLAD M15, we had more than 300 million grid points. And when we go down to nanoseconds, actually, this will be billions of grid points. And they had only 8 sources recorded by 400 receivers. In the first global adjoint tomography model, the data was from 253 earthquakes, where each earthquake was recorded by approximately 1,000 stations. It was a 2D acoustic problem. This is a 3D analastic problem. There, the duration of seismograms was 8 seconds, and in our case, we are routinely computing 180-minute seismograms. And this is not submitted, this is now published. The GLAD M25 model was constructed using more and more data, actually, not 253, but this time more than 1,400 earthquakes was used. And of course, the ultimate goal is to use the entire catalog, just to give you an idea about the size of the problems. So this is the distribution of seismic sources and the stations for the GLAD M15 model. And here you see some results from GLAD M15. This is our starting model at 250 kilometers. So basically you are looking at the shear wave speed structure, where the red colors denote the hot material low wave speed structures such as mantle plumes, and the blue color denotes the cold material, typically subduction zones and the cratonic areas, and with the high wave speeds. So you are looking at the shear wave speed perturbations, which is about 2% in this case, or 3%. And this is the starting model. This is what we got after 15 iterations. Just to guide you through, you see the enhancement of the plume features such as Hawaii or Caroline or Pacific super plume. And here you see the Aleutians, subduction along Aleutians, or the Japan Kuril Islands. And you can even observe Yellowstone here or Galapagos, etc. So if you look at some vertical cross sections, this is one of them from Samoa towards North America. So the ball is the core mantle boundary, and it's a vertical cross section. And this hot region is the low wave speed region on the core mantle boundary is the Pacific superplume region. And this is what we observe after 15 iterations, the upwelling Samoa plume, and this blue dot here is the subduction along Tonga. And if you look at another cross section from in this direction this time in the Pacific, now you see Tahiti plume, and this is the subduction along Tonga Trench, and you see the potential plume slab interaction. And here also you see the Galapagos plume. And of course, there are different theories to explain these mantle plumes. Multi-scale mantle plumes is one of them, like which says that the stable lower mantle plumes in the lower mantle may be followed by smaller upper mantle plumes like this. This change happens at around 660 kilometers or 1,000 because of the change in mantle viscosity, thermal conductivity, thermal expansivity, or the phase transitions. So when I take a cross section from New Zealand towards Samoa like this is the VPVS ratios. You see again the Pacific superplume upwelling, and this is the upper mantle discontinuity, and you see all these nice upwellings in the upper mantle, which nicely coincides with the volcanic islands. And this is the New Zealand geothermal zone. So this might be an indication from seismic tomography for the multi-scale mantle plumes. However, I put a question mark here because this is such a difficult region with lots of earthquakes recorded by, for instance, US array stations, which what we observe here may also be the artifact or partially the artifact of the source locations. So that's why it highlights the importance of resolution and uncertainty quantification. Okay, so as I said in GLAD M25, there is much more data recorded by more than 11,000 seismic stations and 1,480 earthquakes. This shows the distribution of seismic stations. And this is again the starting model S362 ANI. You are looking at the North America, and this is GLAD M15, and this is GLAD M25, where GLAD M15 was the starting model of GLAD M25. So you see the improvement. Basically, after 10 more iterations and with more data, the results did not dramatically change. I mean, we didn't get a completely different model, but you can see that the perturbations of the seismic features become higher, and they are more highlighted, such as you can see Yellowstone much better, and you can see how the subduction along Aleutians is enhanced, etc. And you see all the hotspot regions in North America. And this is another cross-section, a comparison of the subduction along South America. This is M15 and this is M25 at 250, 440 and 660 kilometer depths. And you can see how the subduction along the subduction of Nazca Plate underneath South America is imaged really nicely. You can see the continuous subduction and the increased resolution compared to GLAD M15. And this is a 3D contour image of the subduction. And this is another cross section showing the African plume, African super plume, and this is one of the dramatic differences between GLAD M15 and M25. You see the enhanced African plume. This is afar after 10 more iterations. And I will, this is just a collection of the comparison of GLAD M25 to other models, other global models, both S-wave and P-wave. So basically, it's encouraging to see the agreements between the models. There's kind of a convergence, but of course, there are still some discrepancies as well. So most likely from now on, we need to focus more on the uncertainty quantification problems and the resolution problems. So this image, I don't know how much time I have, but this image now shows the spectral content of the different seismic tomography models. For instance, S362NE, which was our starting model, is a degree 20 model. S40RTS is one of the most commonly used 3D mantle models by Ritsama et al., which is degree 40. So now you see the comparison of M15 and M25 to these two models. So M15, you see how the spectral content changes, how GLAD M15 starts imaging much smaller scale features compared to its starting model. And this is GLAD M25 becomes more comparable to S40 RTS, and actually you can see more energy beyond degree 40. Actually, you need an expansion of spherical harmonics up to 60 degrees for GLAD M25 to fully capture the complexity. And now you can play with all these spectral contents and easily plot these GLAD M15 and M25 models with these toolbox that one of my students developed, and which is just accepted and will be public. Because this is an important contribution, because it's kind of challenging to visualize and exchange our models with other researchers, because you really need to, because these models are originally sampled at the spectral element meshes, but now by expanding them onto spherical harmonics, you can operate and plot and play with these models on your personal laptops. And this is a comparison of GLAD M25 to a normal mode, degree 12 normal mode data from Paula Kuhlmeier. This is just to highlight how GLAD M25 compares to normal mode data, because we didn't use any normal mode data in our simulations. And it is kind of encouraging to see that this is the S wave speed perturbations in the lower mantle, and this is a degree 12 version of GLAD M25 and degree 60 version of GLAD M25. It's very encouraging to see that, of course, the perturbations are different, but there is a quite good agreement in the S wave speed perturbations in the lower mantle. If you make a one-to-one comparison, even you see this red blob here, they correspond to each other. So there's a really good correlation, I would say, except the perturbations. And this is VP, P-wave velocity perturbations, where things become a bit more complicated. Instead of P-wave speed, I here compared bulk sound speed, because there are also discussions in the core mantle boundary structure that there's an anti-correlation between S-wave speeds and bulk sound speeds, which directly tells us about composition, the potential composition or thermal variations in the core mantle boundary. However, it's not that straightforward, because we don't see the good correlation in the bulk sound speed models of these normal mode model and GLAD M25. You can see the discrepancies highlighted with these circles. So that's something, of course, the data coverage of the normal mode data should be much better compared to what we have, because still the lower mantle resolution is suffering from the data coverage problem, but it's worthwhile to investigate further. So this is kind of a comparison by taking the average structure, degree 2 structure of GLAD M25. And these are from the S to P ratio from Paula Kuhlmeier. From the black one is their model. The blue one is a model from another normal mode study, and the red one is from body wave study. So the Kuhlmeier's model uses both data sets. So you can see the agreement or disagreement with the average S to P ratios to a purely normal mode and the purely body wave data. But what is interesting for me is that when I try to prepare a similar plot from GLAD M25, actually the average is much smaller to that of a normal mode, pure normal mode data. So this is something that we are working on with Paula to try to understand what are the causes of these discrepancies between different models. Okay, so I would like to now talk about what we are doing next very briefly. So after this, we decided to include azimuthal anisotropy in the upper mantle in our inversions. So to this end, we are assimilating data from only surface waves using minor arc and major arc surface waves. Here you see seismograms from one sample path for an earthquake in New Zealand recorded by a station in Afghanistan. And we have 2 period bands for this study, going down to a minimum period of 40 seconds. So these are the minor arc Rayleigh waves, major arc Rayleigh waves, and these are the minor and major arc Laue waves. And this is the longer period component. And we have been using frequency-dependent multi-taper measurements as our misfit function. But in this study, we changed our misfit function a bit, and we started looking at double difference measurements, which tells you that rather than looking at the misfit between observed and synthetic at a specific station, we just look at the cross correlation of the synthetic and observed data between neighboring stations. And then we just look at the difference between observed and differential observed and synthetic data. What is the advantage? Well, first of all, you can get rid of the origin time errors of the earthquakes, and also by using such double difference travel time measurements, you can improve the resolution much faster. So it improves the convergence rate of our iterations. So this is just this just shows the travel time pairs for the double difference measurements on different components. Of course, we have the most paired stations in North America, thanks to US array stations. And we performed 16 more iterations starting from GLAD M25. And this figure just shows the misfit reduction. This is the total misfit reduction, but we also keep track of the misfit reduction at different measurement categories. So the jumps or the different colors denote whenever we change the misfit function or the number of measurements, etc., or the measure period bands. So we kind of start from the beginning, but you see that still our misfit is decreasing nicely. And these are some preliminary results after 16 more iterations for the azimuthal anisotropy. So at 50, 100, 350, 500 kilometers. So basically, we observed that the azimuthal anisotropy denotes or well correlates with the plate tectonics or the plate motions. And we can nicely see the correlation with the plate motions. And here, it's kind of a very rough comparison to other models. This figure is from Sheffer and Lebedev, a collection of different models. So which shows significantly different results when you compare all these models, although the large scale features are kind of the same. So now our model also becomes another model which agrees and disagrees in certain regions compared to other models. So we are still exploring what's happening, but at this stage in our model, still we are not there. The model, the azimuthal anisotropy part has not converged yet. We can understand it by looking at the strength of the anisotropy, where still the maximum is around 2% peak-to-peak anisotropy in our model, which is not enough, we know, but we also see that our misfit is still decreasing. So that's why we are still not there, but it's kind of promising to see that we are kind of on the right track in imaging. So when we focus on Europe, this is a comparison to a regional continental scale model. Again, we see kind of a good correlation. For instance, here, the rotational motion due to different, the meeting point of the oceanic ridges, or you can see the counterclockwise of the Anatolian plate, which is in agreement, or this anisotropic pattern because of the Tonquist Struve zone here in Europe it's kind of encouraging to see these kinds of agreements with the continental scale studies. And this is another example from North America at 50 kilometers. This is a compilation of SKS splitting results from Thorsten Becker. Actually, we don't have to see, I mean, the surface wave anisotropy do not have to match with the SKS splitting results because they are sensitive to different, they may be sensitive to the anisotropy in different parts of the mantle or crust. But in this case, we kind of see a nice correlation with the SKS splitting results in North America. Even this rotational motion here around Yellowstone and most likely related to subduction as well, which kind of match nicely to SKS splitting results. And now our goal is also to take our measurements down to Earth's outer core. So this is in collaboration with Dan Frost, Ed Garnero, and Maureen Long. We have this project all together. And Mila Creasy is my NSF postdoctoral fellow, my postdoc in my group. Now she's moving to Los Alamos in the new year. So we have been working together to investigate the Earth's outer core, again using 3D wave simulations. So what are the potential challenges to image the Earth's outer core is that, you know, Earth's outer core has a layered structure, and which makes it important that especially to have a more accurate structure of the first 400, 500 kilometers of the outer core is crucial, because that is kind of controlled by the geodynamical processes, and which would give us lots of insight on the generation of Earth's magnetic field. But the problem, the challenge is that this is such a simple radially symmetric model or just a layered model in the outer core. But we first have to solve the complicated crustal and mantle structure on top of that. We have to pass this zone. So potential problems are the isolation of SMKS phases, these phases that are reflected from the other side of the core mantle boundary. And the finite frequency effects can be important. Of course, 3D mantle and crustal effects, generally, again, mantle corrections are applied, but we don't know their accuracy, and how mantle anisotropy can also additionally complicate such measurements. So this is a figure from Nila. She just looked at these SMKS phases for an earthquake here, recorded by stations here. You see these nice SKS phases. I mean, the record sections are aligned on SKS, but you can nicely see how multiple phases can arrive in the same window. And this is for a deep event. And if you look at a shallow event, because of the crustal effects, the measurements become much harder. The isolation of phases become much more problematic. And right now we are investigating the effect of such complications in the core phases measurements. And this is another illustration where you see the sensitivity of an SKKS and SKKKS phase. SKKS is just bounces back from the other side of the core mantle boundary twice. SKKKS bounces 3 times. And this is a sensitivity kernel computed using PRAM model for this SKKS phase, and this is the S3KS. But in this case, we used a 3D mantle model. The shape of the kernels or the sensitivity kind of remain the same. But what we observe is that the outer core models are the same in both simulations. It's PRAM. But just by changing the mantle model, you also change the sensitivity in the outer core. So basically, you know, that's a good reminder on the effect of the 3D mantle and crustal models, which can be potentially mapped into the outer core in the measurements. So in summary, these are all our efforts to improve the resolution of Earth's interior, starting from Mantle, but now we are slowly moving into the core. And the ultimate goal is to use all available data from all earthquakes and all seismic stations. And of course, to be able to improve the data coverage, we also need to start using data from other potentially good receivers. And we need to also take into account better physics in our inverse problems, like adding azimuthal anisotropy and attenuation and elasticity actually on a side on a different set of iterations. We are also trying to construct the inelastic structure of the Earth's mantle. And but of course, while we are performing all these efforts, we need to keep an eye on the resolution, uncertainty analysis, and data coverage problems, which I think the three major problems right now of the global seismology that we need to spend more time into. Thanks very much. Actually, here I have this movie. Maybe I can just start the movie while you are watching. I can take questions. This movie just shows the shear wave perturbations of the mantle plumes. And you are going to see in the background running.
Hi, thank you for your presentation. That was actually a great talk, and the graphics are amazing. I have a question. It's more like a curiosity about the SpecFEM simulation for Mars.
Mm-hmm.
Like, I was always curious to see, because there is a big, the Olympus Mount is like 25 kilometers. What the waves do when they get there? Like the interaction with topography, that's what I'm talking about.
Well, I don't have such a figure here, but it depends, of course, on the period, the resolution of the simulations, etc. But definitely, we know that topography has a huge effect, which has to be taken into account. And that was again one of our goals when we implemented these, when we started implementing Mars models into SpecFEM, where we take the topographic variations into account. Definitely, there is an effect of the Mount Olympus, which needs to be taken into account, but I just don't have the right paths to show you. Maybe later on I can.
But
exactly
have you looked like specifically to the dome, to the mount, to the if you see like, I don't know, some sort of topography effect, like reflection? Sometimes the topography, actually the topography could like amplify the motion. And I was curious if at 25 kilometers. So you haven't looked specifically to the Olympus Mount?
I haven't looked.
Okay.
No, I haven't, but definitely we can look.
And so your simulation has a resolution to look at this possible interaction?
Sure. Actually, the movie I showed you has resolution down to 17 seconds or 15 seconds. And actually for regional simulations, we can go down to 1 Hertz as well to observe all these effects.
Okay, thank you.
Maybe later on, when I have the appropriate simulations to show those effects, I can share with you.
Yeah, that would be great. Thank you.
So, Ebru, thanks for the talk. You did cover two things that I was interested in at the very end when you were talking about including attenuation and the source functions of earthquakes. I was wondering, you just rely on a low pass filter to get rid of the source function at this point?
At the moment, our source time function is a simple Gaussian. We just use the Gaussian source time function with a half duration of the earthquakes given in the CMT catalog. Sometimes we update the CMT parameters except the half duration because we don't have really great resolution. But of course, especially when we would like to go down to shorter periods, we need to address the source time function problem, especially below 9 seconds. Right now, what we do is that we choose our earthquakes in a way to make sure that the point source approximation will still be valid. And we try to choose relatively simpler earthquakes or the rupture processes to try to minimize any uncertainty that would be introduced because of the lack of proper source time functions or other parameters.
So for I've been really interested in non-anisotropy, the attenuation of elasticity. If you look at different kinds of models, there are always phase shifts that are in those models depending on what you assume. And
Yes.
it seems like, and for regional waves, when we've computed some of these things up, they can be quite large and they trade off with the velocity. What sort of research can we do to actually constrain anelastic attenuation?
That's a really great question, actually. This has been where we spent quite some time. And indeed, you are very right. All the elastic models, unfortunately, I wish I had those figures. I didn't present the anelastic preliminary results with you, but let me see if I have some of the results of my student. Unfortunately, it's not here, but indeed, you are very right. Every elastic model is perturbed around an anelastic model, right? So the phase shifts, phase perturbations, they are shifted towards the reference anelastic model. And so far, we have assumed that a reasonable 1D Q model is good enough to capture the phase shift coming from the physical dispersion term of anelasticity, right? And which is true, most likely, for most of the regional or continental scale studies. But at the global scale, this was something that one of my students did very quickly. He just changed the, for instance, upper mantle attenuation. He used PRAM, but he just changed the, this high attenuation zone, low velocity zone values with a different Q value. And you can see the dramatic difference, dramatic shift in surface waves, which becomes really terrible for major arc surface waves. That makes sense. But you can see up to 20 seconds time shifts just because of a simple shift in the Q structure. So actually, that's why the solution is that we have to invert both elastic and inelastic parameters together. And that's the only solution. And indeed, we don't have to invert them simultaneously just because we want to construct a new anelastic model, but we need these simultaneous inversions to be able to further improve the elastic structure as well. Otherwise, we will keep introducing the bias coming from our reference anelastic model. And you are also right that since all the elastic models are just some models based on a reference anelastic model, I think we should also be careful when we are publishing our elastic models. We have to make it very clear that our phase shifts, our phases are with respect to this model, because it also creates lots of confusion when you compare different models. Because when you put two models next to each other, if you don't define how they were constructed, then that introduces some bias in our interpretations as well. So my solution is what I can offer. Of course, this is not going to be an easy solution, but we have to invert them simultaneously, both elastic and inelastic parameters.
But how do you actually, how do you choose the correct parameterization for the anelasticity? I'm not sure we know enough yet to do that.
That's true. That is very true. At the moment, we, of course, we like to try to minimize the assumptions as much as possible, but we have to make some assumptions. Otherwise, there is the trade-off between the parameters. Of course, we ideally would like to invert everything at the same time, but the trade-off between parameters makes it really challenging. So we started with our elastic parameterization again, like transfers the isotropic parameterization. We started from GLAD M25, and together with the elastic transfers the isotropic parameterization, we just added the shear Q as the anelastic parameter. So it's just one more parameter. We ignore the attenuation on P waves right now, or the QP. We just ignore it, or kappa. Just because to simplify the problem, that doesn't mean that it doesn't exist, but most likely in our problem, the dominant parameter will be the shear Q. So this is how we make some tests. And also in collaboration with Daniel Peter, one of his students, while I try to attack the real data, one of Daniel's students is currently he's set up a purely synthetic experiment to see how well we can recover the Q structure using a realistic data coverage like what we are using in our global inversion. So I think we are going to have some nice results summarizing our observations, both on synthetic full 3D experiments and then applied to real data. Hopefully soon I can show, maybe in another talk, I can just fully focus on analasticity and present all these preliminary results. But you are right, I don't know what is the right way. We are just trying to find our way by trial and error, and trying to introduce some better physics and see what will happen. But these 3D synthetic tests will give us a good understanding, I think, about what we can really do, what we can't really do. It is at the global scale. Any other questions?
Yeah, I have just one more question.
Sure.
That's because I'm kind of ignorant about Mars, but how you, and probably I missed that. So we have a topography map of Mars, right? We do have a very good topography, I think. So how you, you figure out the material properties, like the structure is?
You mean the subsurface structure?
Yeah, yeah.
Well, actually, right now we are still only, I mean, the radially, initially, we were just using the proposed radially symmetric models from other measurements like gravitational or moment of inertia, etc. So now we have the inside seismic data. So that's why all these reference models are now being adjusted with the seismic constraints. So these are mainly how the structure or the wave speed variations have been determined. But before inside, it was mainly from gravitational or surface geology and the moment of inertia studies.
Interesting. Okay, thank you.
You're welcome.
Any more questions? Okay, I think there are no more questions. So thank you, Dr. Bozdag. Thank you for the wonderful presentation. And
Thanks very much.
Thank you everyone for participation.
Bye-bye. Thank you.
Bye-bye. Very nice to meet you all. Bye-bye.
guys.
Thank
Thanks.
you.
Bye.